Welcome back to Calculus 2, section 8.5, where we uncover 4 tests for testing convergence and divergence of series. So we'll talk about ratio, root, and comparison tests. And again, if it converges, we don't know what the sum converges to. The only 2 tests where we can tell are geometric and telescoping. So those are the only 2 tests where we know where the sum converges to. We have a way to compute that. So now, if it converges, we don't know what it converges to. If it diverges, obviously, it's infinity. Comparison tests, in the scheme of all things, will be left as the last resort. So you will go through and try to use anything else, right? And then if you have to, right? If nothing else fits from those 8 tests that we cover, then you use comparison tests. And you would usually use the limit over the direct one, because the limit you don't have to do the proof, where the direct one you would have to do a proof of some sort. So we'll see all of that. Each one of these tests, again, is used in its own special realm, right, of problems. So we'll see that as well. We'll start with the ratio test. So ratio test, you have some general series that can start at 0, can start at 1, can start anywhere. All right, can start anywhere. And you can see this AN. It's really generic, right? So this is how ratio test works. You take the limit of AN plus 1 over AN. All right? As n goes to infinity. And this can give you 3 possible answers. Now, this is what you have to memorize. If you get a finite value smaller than 1, so negative half or 0.8 or something, or you can have the limit to be equal to 1, or you have the limit to be larger than 1. So these are your 3 options. Just need to log into the textbook. I forgot to do that at the beginning. I'm going to take a second. There we go. Okay. All right, so you have a general series, AN, whatever it is, and you will find the limit. I forgot the absolute values here. Oops, sorry. Absolute values are very important. You will see that for power series. Absolutely have to have these absolute values. And you can have these 3 possible results. The limit is less than 1, in which case we have a convergence. Limit is larger than 1, in which case we have divergence. And then if the limit is exactly 1, test is inconclusive. You have to use a different test. Okay? I'm sorry? Well, you might decide to use this test on a series, and you get the limit 1, right? So this is just an option for it. If it happens, you know that you are supposed to use a different one. That's all it is. So that's all we have. This is what you must memorize. It is on the sheet that I gave you under the ratio test. And a cool note over here would be that this is a go-to test if you have factorials around. Remember the factorials? The n, right? You remember that one? All right, good. So use it for factorials, and I'll just put n factorial. Now, you can use this for other stuff as well, okay? It's okay. Geometric series is going to work here, all right? So this test is not only for factorials. But if you have factorials, this is the way to go, unless you can do the divergence, right, and show it diverges if you have factorials. So ratio test is very simple to do as long as you know your limits, right? So review the L'Hopital's rule from 4.7 Calc2 and or 4.8, whatever it is. I think it's 4.7. And the rest is just limit, 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 taking limits. So let's take a look at, I don't know, 2-3 examples. All right, so let's take a look at, for instance, summation of, I don't know, 3 to the k divided by k factorial. Let's say k starts at 0, goes to infinity. I can start with any value. So looking at this, the ak is equal to 3 to the k over k factorial. And then we need ak plus 1, which is going to be 3 to the k plus 1 over, open parenthesis, k plus 1 and everything factorial. So this is the setup for us, right? We set this up, and then we just pull it into the limit and work out the algebra, and then eventually take the limit. So we're supposed to check limit as k goes to infinity, the main division line. Don't forget the absolute values. So 3 to the k plus 1 divided by k plus 1 everything factorial divided by 3 to the k over k factorial. Now all of those factorial rules that we learned are going to play the role, right? We're going to have 3 times 3 to the k divided by k plus 1 times k factorial. So what I've done here is I took the 3 to the k plus 1, and I peeled off one of the 3's, right, which is the plus 1 deal. And then I used the formula for factorials. Remember that 5 factorial is 5 times 4 factorial, or 11 factorial is 11 times 10 factorial, because 10 factorial contains all of that 1 times 2 times 3 all the way up to 10, and then if it's times 11, it becomes 11 factorial. So I can write 11 factorial as 11 times 10 factorial. So what I did is I peeled off those extra plus 1's. Now, division of fractions, right? So I'm changing into multiplication and flipping the second one. If you change division into multiplication, you have to flip the second fraction. And now you see the whole bunch of stuff cancels. Ratio test is awesome like that, right? All of these scary terms cancel, and you get to take the derivative of a simple, right? The limit of the simple stuff. So you have 3 divided by k plus 1, right? And as k goes to infinity, the whole thing goes to 0, which is less than 1, which implies convergence by ratio test. And that's your answer, right? You have to, remember, you have to state which test you used. Yes. I said it? Oh.
I was going to ask, like, similar to the first derivative test, they mentioned this test that you solved it.
Yes, you have to say, so for the entire chapter 8. Because your exam is going to be like this. Test for convergence and divergence and 10 of these on a pile, right? Same like your second exam for integrals. I never said use integration by parts, use the trig sub, right? You knew what to do because you studied and you have the experience, right? You will have the same thing with these things. You see a factorial, right? You say, hey, ratio test. Let's take a look at another example. Yes?
If we look at that, like in terms of the growth rate though, and it's still, you have like, faster over slower, right? Like in terms of growth rate.
Faster over slower would always, yeah, but that works only for divergence tests, right? In this case over here, you have slower over faster, because factorial is faster than exponential. It goes ln's, and then polynomials, and then exponents, and then factorials, and then n to the n is the boss. Right? So this was definitely slower over faster, limit is 0, and the divergence is inconclusive. Therefore, right, can't use it. Next example, however, is the one where you can claim your faster over slower, right? Because if you have summation of k to the k divided by k factorial, you see, start at 1, go to infinity. Now, this is the one where divergence test is immediately involved. You use divergence test and you're done, right? You have a fast over slow, it goes to infinity, limit is not 0, divergence test kicks in and says this diverges. Done. So this is a problem that you just look at and you know the outcome, and you just need to write that. You just need to write that out, that the limit of k to the k divided by k factorial is equal to 0 by growth rate rules, and then you just say diverges by divergence test. That would be your answer on the exam for this question, right? Now, I want to go through ratio test now because we can, all right, to also show divergence, right, because our limit needs to be more than 1. And I'm going to use the ratio test just to, again, show math skills, to show how ratio test works. But then on the exam, this is the divergence test. You know, you just write one line, you're done. So AK is k to the k divided by k factorial, AK plus 1. We need that, right, next term. Okay, so it's k plus 1 raised to the k plus 1 divided by k plus 1 factorial. So you have to increase everywhere. Now, as you do that, k goes to infinity. This time I'm going to skip a step. We're going to write. No, I'm not going to skip a step still. That's right. K plus 1 raised to the k plus 1 divided by k plus 1 factorial divided by k to the k over k factorial. There we go. Equals to limit k goes to infinity. And now I'm going to peel off. So we have k plus 1 and then k plus 1 to the k. Can't fix that. Divided by k plus 1 and then k factorial times, flip the other one, which is k factorial over k to the k. Okay? Now these guys cancel, right? And then we have these guys cancel as well. Leaving us with limit k goes to infinity. We have k plus 1 to the k divided by k to the k in absolute values. What now? Anyone? Nope. Nope. What now? So now we're in Calc 1. Welcome to Calculus 1. All right, who can solve a Calc 1 problem? I cleared Calc 2 for you, all right? Actually, I cleared the algebra for you. No. No. See, if you leave the coefficients, you will get 1, and the test is inconclusive. Matt is dying in the back. He's like, So how about we pull the k exponent together? We don't need these absolute values anymore. How about now? Getting anywhere?
It's like 1 plus 1
Okay, we can do that algebra. You want to divide k through? Sure. 1 plus 1 over k to the k, okay? What is this? E! The definition of E from Calculus 1 and Calculus 2, Chapter 6. Which is bigger than 1, which means diverges by ratio test. But as I say, no one sane would do this, right? You just do the growth rate of functions, it diverges because, right, it's faster function over slower, you're done. Are we good with ratio test? Or you want one more? There are actually students in this classroom. For those of you listening in. One more. That's all I need. One brave soul. So, let's see. How about, this looks like an awesome question. 2 plus 4 over 16 plus 8 over 81 plus 16 over 256 plus dot dot dot. Does it converge or diverge? Oh, you first have to put it into a sum and formulas and all of that kind of stuff. So we'll figure it out. It's a good question for the test. I have a moment with fix.
You're not using your hungry.
What?
You're not using your hungry. That was it. No.
It's a little commercial, I know. Why it's not so quick?
That was the wrong candy. Put right or left. I thought you was about to do the bottle flip thing. You ever seen that? No. Here, flip. You want half? No, I want the whole thing. Half a person. I'll get you one next time. Yeah, I did. I did. You start to tell me. Alright, thanks, fun. We have to remember this one. I'm not gonna remember. Yeah, exactly. I have a gun. And I'll like give you some extra seasoning for me. I'm sorry, this has to be done. My fool.
the sequence of numbers on top, sequence of numbers on bottom. The exponential, polynomial progression, the factorial progression.
I'm waiting for someone to fall to the side so that they can be ready for the mistake. Wait, how to buy seat. That's better than the other one. So. Not gonna be A plus 1 on top. A plus 1 on top is what? I just picked a random problem, hoping I would be able to do this. This is very random.
Should we use ratio?
Yeah. Yeah, now use something. Do what?
That's what we should use ratio.
Do
Each thing times 2 on the bottom, it's, I have no idea.
I mean, that's the question.
You have 4 terms, should be sufficient. You don't need to figure out any more terms. All you need to do is to compress this into a sum that will have a formula to it and then unleash ratio test upon it. Let's see. We're going to write 2 over 1 over here. So what is this summation? The top goes 2, 4, 8, 16. That looks like 2 to the k, where k starts at 1. Right? Now the bottom says 1, 16, 81, 256. K to the 4th? Is it? Like this? Ah, well, we're done. Goes to infinity. So now, do we have this? We know that AK is 2 to the k over k to the 4th. AK plus 1 is 2 to the k plus 1 divided by k plus 1 to the 4th. And compile the limit, take the limit, and be done with the problem. So what's the limit over here? How cool is this? They all left home, actually. I'm alone. All right.
So do you graph these?
No,
No. Like ever?
these are sums. So it's either a finite value, 7, or infinity. There's nothing to graph. It's just a number. Or infinity.
Oh, I meant like
The sequence?
yes.
You can graph sequence. Yeah, that was we did that. 8.1, 8.2, where you just graph and you get the dots. Root test. So your sum that could start at any value should look like this. The entire sequence should be raised to the k. And how the test looks like? You take the limit as k goes to infinity of the kth root of ak to the k. Obviously, they will cancel, right? And you have 3 possibilities. Limit is finite and less than 1, convergence. Limit is equal to 1, inconclusive. Limit is larger than 1, divergence. Same conclusions like the previous test. Yes?
On our formula sheet, there's no like race to the K for the original.
Yeah, because it's kind of included in AK on the formula sheet, but you will see as soon as I do the example what I mean by this. So let's just do the most trivial case of all cases, which is k to the k starting at, let's say, 1 and going to infinity. All right, let's say this is the problem. So now, in this case, ak to the k would be k to the k from where ak is just k, right? But the way you do this is you would say limit as k goes to infinity of kth roots to k to the k is just limit k goes to infinity of k, because those two cancel, and you just get infinity, which is divergence. Now you know that looking at the k to the k is going to diverge by divergence test, right? Because limit is not 0. But then you can do this as well. Did this make any sense?
Yes. I just don't see why it's important to have those ones where in the power.
Well, they cancel, right? Oh, in the definition over here, you mean? Well, we put them there so you see that you will be canceling those. Maybe I should take the orange and kind of cancel them like this. The trick is that it's not always easy to extract AK and separate it from the K exponent. That's not always. Sometimes algebra will be a little bit tricky around that. But it's not impossible. Let's see other examples. So this one should be obvious. Should be. Summation of 2 to the k over k plus 1 raised to the k from 1 to infinity. So what should I write? Limit k goes to infinity, kth root of 2k over k plus 1, everything to the k. When these guys cancel, all we're left with is 2k over k plus 1, and then what happens? Anyone? What's the limit? Okay, so far I heard 1, 2, and infinity. Want to take it outside or what? No, please, Vincent, just... Yeah. Exactly. Very good. So diverges, right, which is larger than 1, diverges by a root test. Done. How about this one? What happened? Look at this one. Converges to infinity. Yeah. Contradiction in terms. What's the verdict?
That's not close to E. Oh no, wait, I got 0. 1. I got
Nope. It diverges, but.
Yes.
I got 1.
I see.
Yeah, gotta be E in it. Good. It is some form of it, but
That's 3.
Oh, yeah. I got it.
what does this mean? It's not 3, but
Is that not a 3?
that's a 3. That's how you write 3.
I can't see.
Here, you want me to translate this into Babylonian here?
It's right there.
That's a 3. All right.
What is that?
This is number 3 in Babylon. You want Mayan here?
Why do you know that?
Because it's cool. Roman numerals.
Okay, I know.
Give us more.
I'm trying to remember Egyptian. I think it's staffs are ones. I think staffs are ones. I know astonished man is a million.
Oh, wait. Oh. I think I get it now.
Chapter 1.
Do share.
I think I'm wrong, but I think I get it.
What is it?
Wait, what?
What is it? Tell us.
Oh. What? Oh, okay, I get it now.
Sonia knows she did it. Do you all remember compounding formula from your precalculus? You remember how it used to be 1, well, P times 1, and then R over N to the NT, and then how your E formula was PERT? Do you remember that? So now if you just get rid of the T's and you get rid of the P's, do you see that R at work? Let me write a whole thing one more time with something that you are familiar with. So your formula for compounding, if you remember, was 1 plus R over N to the NT. The continuous compounding was A equals PERT. Yeah, PERT. So now, what am I going to do? Kill the AP part, and then kill the T part, and you see how this R is this? You also know, hopefully, that 1 plus 1 over N to the N is E to the 1, because that's that. Are we all green on this?
Yeah.
Excellent. One more example of root test, because you're so good with algebra, and we'll move to something else. All right, good luck with this one. That's what you get when you look at the problems. You have no clue how to solve it. Put the hook somewhere together.
What's the point? You said to put a limit. You said to put a limit. It's 1 to 10, so it converts. Yes.
Oh wait, doesn't any, like ln of anything over, doesn't that become like less than 1 so it converges?
Oh wait.
Yeah.
It's gonna be everything off.
Well, because it's ln of, because it's gonna cancel out from ln 1 over infinity.
It's gonna be 1 over infinity. Yeah.
Yeah, so that because it's less than, because k, alright, look. So like, here's the limit.
Okay, to be fair. Well, that's what I'm saying. So as this is going to infinity.
Oh wait, no, it's going k.
That's what I'm saying.
Oh shit. Well, it's the same as infinity.
It converges to
Well, it doesn't have the same version.
1 over ln k plus 1.
I wouldn't be if that was like a misspell, like you didn't mean to do that. Like you meant to 150.
Yeah. So like, it's just you're plugging K. Yeah. And you get the same thing. Yeah. You get the same thing. You get it converges to that, right? I guess.
It doesn't converge to it, it just converges. It doesn't tell where it converges to.
Oh. Oh, that's right. That's right. This is not testing what it is.
Yeah.
But we don't know what K is.
So no one can 0 implication. But that's it.
I guess that.
I mean, it's a variable. So no, 1 over ln of k plus 1.
Actually, are you going to the number that's left?
What?
Professor, you got 5 minutes left.
No, I don't. I have whole lifetime. Unless you have some other plans for me, I don't know. Should I be worried now?
No.
Okay.
I mean, but after that quiz policy, I don't know. Don't play your card.
After everything I've done. So you will recognize when to use the root test, right? When everything is raised to power k, you can cancel it off, right?
Yeah.
Just study. That's
No, it goes to k.
Oh,
Yeah.
No, it should go to k, right? K goes to k.
then can you just say
how much is 1 divided by infinity? Hey!
But how does it go? How does the limit goes to infinity? function goes to k.
Well, that's supposed to be infinity over there. Yeah, we deal only with infinite series. You should have spotted that right away. And,
I told you, it's K, so you got it.
yeah. Yeah. So we'll all put this past and move to comparison tests. Apparently I only have 4 minutes left.
Plus 10. Plus 10.
Comparison tests, I will put this as a last resort. Yeah, when all other options run out, then you compare. So there are two comparison tests that we're considering: direct comparison which involves that proof, and limit comparison, which involves limit. Most of the time, limit comparison is a better choice because, not because of the proof. Proof is very easy. It's because there's way too many things going on with the direct comparison. So let's take a look at the direct comparison. Chewbacca is with us, I see. All right. So let's start with a comparison test. Direct comparison first. Direct comparison. So let summation of AK, I can't write anymore, and summation of BK be series with positive terms. So that's what I have. In this case, 1. If AK is less than BK and summation of BK converges, then summation AK converges as well. 2. If AK is larger than BK and summation BK diverges, then summation AK diverges as well. Now this might be a little bit convoluted, but let's take a look at the actual explanations of this using the graphs of sequences that are involved. So for the first one, this is your n, this is your an, right? Input n is always 1, 2, 3, 4, 5, and so on. So now what's happening? For the first one, you have some, you are testing AK, obviously, right? That's the one that you're testing. So you have some crazy sequence that doesn't fit telescoping, doesn't fit geometric, can't use ratio because it went to 1, can't use root, it went to 1, right, inconclusive. The limit is 0, so nothing works, all right? It's just crazy like that. So what we can do is kind of use the squeeze theorem idea, where you come up with the convergent BK. All right? So sum of BK is going to converge, but BK is trapping AK completely between the x-axis, right? The N and the BK. So because the sum of BK converges, it forces AK to converge as well. Summation of AK to converge. So a sum of AK is trapped within the sum of BK. So this is what the comparison means. Now, where is the proof that I mentioned? Well, remember that you pick whatever BK you think is going to work. And this is where P-series come in. But then, because you picked that BK, you have to prove that this holds for all K. So this is what you would be proving, that BK is always larger than or always smaller than AK. In order to, so you will have to develop some kind of intuition for this and figure out whether it's right, always smaller, always larger, so you can claim convergence and divergence. The second one is the same, except you are looking for BK that it's smaller than AK, which will push AK into divergence. So we have, again, whatever the sequence is, again, crazy, doesn't fit patterns, doesn't do right much good. But then you come up with a divergent BK, right? Some BK would be divergent. And then that pushes out summation of AK to be divergent as well. As soon as you prove the condition that AK needs to be larger than BK at all times. You find divergent BK, obvious, sum of BK, you should put. So that takes care of that part. So now, let's take a look at one of the examples and then prove our statements here. So say you have this example. Summation infinity goes 1 k cubed divided by 2k to the 4th minus 1. All right. So now you're looking at this and you say, if I try divergence test, on this, the limit goes to 0, right? Denominator is larger. Therefore, divergence test is useless, right? Can't make any conclusions from divergence test. It doesn't fit anything. No telescoping series, no geometric series, definitely not rule, definitely not ratio, right? So what do? You say, well, if I stand sufficiently far away from the problem, this kind of looks like 1 over 2k. Do we see that? Kind of forget about that minus 1. K cubed and k to the 4 will cancel, and you kind of get 1 over 2k. Now, 1 over 2k is technically 1 over k, and we know that diverges. So the gut feeling here is that this should diverge. So what I have to do? So this is, guys, this is the way of thinking that you have to develop, right? You say nothing matched, so I'm going to do comparison. Now, what should I compare it to? Well, you can compare this to anything in mathematics, all right? Anything. But then you say, well, hold on, this is k cubed over k to the 4th. That sounds awful like 1 over k, right? So you come up with, well, you know that AK is exactly k cubed over 2k to the 4th minus 1. And you come up with BK as 1 over k, whose sum by P-series diverges. So now, because of that, right, because of that cancellation you made, and this is similar, not the same, similar, you say, maybe I can compare these two, but remember what I need. I need that condition for divergence that AK must be always bigger than BK for all n k across the spectrum, right, from 1 to infinity. So now, need to prove that AK is larger than BK for all K. K starts at 1 and goes to infinity. Now that is a very easy proof because all you need to do is to do some algebra, right? So that needs to be, this needs to hold. If you can show that this holds, you're done. All you need to show that this holds, and then by the theorem up there, since sum of BK diverged, sum of AK must diverge immediately. So that's what the comparison test is all about. You figure out what to compare it to, and then you do this proof here. Now, how you do this proof? Just cross multiply, right? So you get K to the 4th to be larger or equal than when you multiply across 2K to the 4th minus 1. Bad choice, right? Do you see it's a bad choice? I need to add the 2. Would that change any divergence or anything? Absolutely not. Would it help us in our proof? Of course, because you have 2K to the 4th, 2K to the 4th, and this one has minus 1, and that's a smaller side, right? So it holds. True. We're not stacking the deck, guys. You can put any coefficient in front. Remember that 1/2 can be factored in front of the sum. This will still diverge because if this is infinity without the 2 over there, when you multiply infinity by 1/2, it's still infinity, right? So that 2 really doesn't change any of the conditions of the problem. It helps us actually do the proof and show that this holds. So now you write the answer. And answer goes, since AK is always larger than BK for all K, and summation of BK diverges, the sum of K cubed over 2 to the K4 minus 1 diverges by direct comparison. That's the answer. And there's the entire problem. You looked at the problem, you decided that it would be 1 over K would be a good value. You know harmonic series diverges. You are expecting divergence, and because you are expecting divergence, you are trying to prove that AK is always larger than BK. It has to be that sequence for thinking. You can't go and say, let me prove if AK is bigger than... No, you have to look at the problem, decide what are you comparing it to, and then whatever you're comparing it to, does it converge or diverge, which actually dictates whether you have AK bigger than BK or BK bigger than AK. Right? In one case you're getting convergence, in the other you're getting divergence. So that's the trick of the direct comparison. You always have to do this proof to show. Because, guys, you're making a guess up there, right? You make a guess. Now, if this doesn't hold, you have a wrong choice or you have a wrong concept. Or it doesn't work at all, try the limit comparison. Limit comparison, on the other end, is easier because all you need to do is to take the limit of the ratio of BK and AK. So that's in some sense easier than doing this proof because you are used to calculus limits and you are not used to algebra. So limits should have no issue. Yes?
Are there times when the limit comparison won't work and you have to be direct?
The other way around, most likely.
Okay.
The limit comparison test works most of the time, where the direct one would not. And I will show you why. Let me just write the limit comparison real quick. So again, let summation AK and summation BK be series with positive terms, right? So all the numbers are positive, and we are considering limit k goes to infinity of AK over BK, which we have three cases. So limit is finite. Pick any number, 0 to infinity, any finite number, 0 to infinity. So if the limit is finite, then both sums do the same. What this means, if one sum converges, the other one converges. If one sum diverges, the other one diverges. If it's equal to 0, second case, if it's equal to 0 and summation BK converges, then summation AK converges. And if it's infinity and summation of BK diverges, then summation AK diverges. Three cases. Now, why I'm going to really quickly show identical example, well, similar example to the previous one. Remember what we have? We had k cubed divided by 2k to the fourth, and now I'm going to put plus 1. So the problem is almost the same as previous problem, right? Except now I have plus 1. This is still going to diverge, but the trick is that you cannot do the direct comparison, because in the proof you need minus 1, right? And you will have plus 1, and plus 1 is going to be opposite sign, so it's not going to hold. So you try maybe direct comparison, you see it doesn't work, so then you go with the limit comparison test. The limit comparison test, you have your AK is k cubed over 2k to the fourth plus 1. You choose your BK, we already know, right? 1 over 2k, which is summation of BK diverges. It's a harmonic series, right? We memorized that 1 over k diverges. Now that 1/2 can be kicked out as a coefficient, just like in derivatives and limits and integrals. Kick it out. So now, direct comparison won't work, but the limit comparison will work. So you take limit of AK, which is k cubed, divided by 2k to the fourth plus 1, and you divide that by 1 over k, as k goes to infinity. As soon as you do this, you get limit k to the fourth, right, when you multiply two that are far apart. Actually, let's do 2k. So 2k to the fourth divided by 2k to the fourth plus 1. Multiply two that are close by and put in the denominator. So now we have this, and when you take this limit, what do you get? You get 1, right? And that falls in the first category here, where limit is finite. Both series do the same. So answer, since L is equal to 1 and summation BK diverges, the sum k cubed over 2k to the fourth plus 1 diverges by limit comparison test. And that's the answer. So just a small, tiny change from -2 plus 1, everything else looks the same. Immediately you can't use direct comparison because on that proof, the sign would be the other way. You can't fix it. There's no way to fix that. So you will have to use the limit comparison for this. It's a very subtle difference. So this is why, in a great, scheme of things, you try limit first. All right? Because the problem will most likely work much faster with the limit comparison. Unless the problem on the test or the final says use the direct comparison because you should shovel some algebra around. That's it for today. Next class we'll do 8.6 alternating series, and we will also work on the chapter 9, 9.1.